linear algebra, which is on the basics of data science, which we see soon on this channel. So, but as I want to learn linear algebra and all those things which are required for data science, so I've prepared this blog after learning a lot from a very good Udemy course called Krish Naik. So I'm also starting the course. So I thought like the blog is out, so let's do the YouTube also. So this is regarding the YouTube. If you prefer blog, I will give the link. The blog is there. I've written two blogs, linear algebra 1 and linear algebra 2. Let's see how much I can complete in this YouTube video. Okay, so linear algebra is a branch of mathematics that deals with vectors, vector spaces, linear transformation, and systems of linear equation. It provides a framework for understanding the properties and operations of this mathematical object, which can be represented using matrices and vectors. Okay, this is the fundamental concept of machine learning, deep learning, natural language processing, and many other fields of data science, like the popular one Gen AI. So even Gen AI, you need this thing. It is essential for understanding how algorithm works, especially in those involve optimization and transformation of data. So application of linear algebra, data representation and manipulation, vector and matrices are used to represent data in various forms, such as images, text, and numerical data sets. We are soon going to learn a lot about them. We will take one example to understand. We'll take one example to understand. Let's consider we have a data set for data science. We need to create a model which will be able to predict something. So this data set we are going to take is called house price data set. Okay, so house price data set is there. Here we will have a feature as shown in the images, like area of the house, okay, number of rooms, and the location. Okay, and finally the output will be price. So based on these three things, area, number of rooms, and location, will get the price. Okay, so as you can see, so the area is 1200 square feet, which is like in India we have like this. So two number of rooms. Then Bangalore location is Bangalore, and it will cost you 55 lakhs. Same thing, 800, area is less, two rooms Mumbai, because we know Mumbai is costly, 85 lakhs. Similarly, 1600 square feet to Noida. Noida is even a bit cheaper than these two companies of 55 lakhs. I'm just estimating this. These are not real numbers. So this price thing, we are not going to do. This is the thing which the machine is going to do. This is the thing which we are not going to do. We are only going to give this data set so much. Like we are going to give this data set in number of lakhs, number of 100,000, so that this price will automatically be deducted. Okay, so it will understand, okay, if there is a 1200 square feet 2 BHK in Bangalore in this location, so maybe the location also we can specify, like Kormangla and all those things we can specify. So in Mumbai we can specify like those things. Okay, so then we are going to learn. Okay, so then like Andheri is there, or South Mumbai is there, or Lower Parel, and all those things are there. Okay, so now as it is written here, so that it is also written here, let us have 1000 data sets of the same. Okay, so, and the input will be the output is the thing which we are going to get. So that is what data science is all about. Okay, as a human being, our brain is so well trained that we know that if area of a house is more, the number of rooms are more, and the location is a tier 1 city, the price is going to be high. So in this case, but if we are doing a training of a model from scratch, it doesn't know all these features. Okay, so we have to train it. How we train it? To feed it more data, and it understand is, and all of it understand is the numbers of how the relation of all this input feature is with respect to the price. Okay, so this data is represented to the model in form of vectors. Okay, uh basic definition of the vector is it's a list of numbers. The location can be converted into numbers. Okay, so the basic definition is vector is a list of numbers. Okay, based on the list of vectors, we have the price that is included in the particular vector. Based on the list of vectors, we can see that the model will able to even qualify the relationship between area and the price, because the price is output of the feature, between the area and the price, because the price is output of the feature. Okay, uh, it can quantify the relationship between area and number of rooms, even the area and the number of rooms. Okay, between the area and the number of rooms, and all the other features also it can do. Okay, this is known as the concept of covariance and correlation, and we will look into it later on. Okay, so this is just the basics of linear algebra. So here we see the data representation and manipulation. So when we are training all these specific model, we basically represent the entire data in the form of vector. So here linear algebra provides the tools to represent and manipulate data in the form of vectors. Whenever we talk about vectors, they can be single dimension, two dimension, three dimension, One important thing is that human being, whatever we say, two dimension, that does a basic. What does that basically mean? One dimension, two dimension. So two dimension means this thing. This thing is two dimension, x axis and y axis. We design a coordinate system in which we can have output features of price and inner area. We can see that total plot. This is the two dimension. Okay, x axis and y axis. So 1240, 1245 is what? 1200 is this, and 45 is the output. Okay, 1200 is the area and 45 is the output. Area and the price we have written. So this is the two-dimensional data. Okay, so and we have mapped various things. So maybe we have 10, 15 data. So we have mapped various things. Now we might be thinking that we can draw a three-dimensional vector also. Okay, three dimension. Yes, we can below images x, y, and z axis, or z axis as it is known in the US. Okay, x axis and z axis. I will do the z only because we call it z. So, like in that x, y, and z axis, we have this 1245 and 2. 1245 and 2, we're representing the area, price, and the rooms. Area, price, and the rooms. And we can like have three dimension. As a human being, we can see only three dimension. Okay. So that is also something we should consider. We cannot see the fourth dimension. Okay, linear algebra works very well with higher dimensional data. This is another thing which is there. The vector calculation that can be done with respect to the high dimensional data, it gives us a fabulous result with linear algebra, and how that will happen, we'll talk about that in the future. Higher dimensional data also we can work. Okay, high dimension means more than three dimension. Let's see that we have 500 dimension, which is basically means 500 features in linear algebra. That is what I'm saying. In linear algebra, we have a concept called dimensionality reduction. Okay, this feature, when we apply, try to reduce the dimension so that our 500 dimension data can be to two dimension or three dimension, which us human can understand. We cannot go beyond three dimension. Okay, so 500 dimension data is nothing but 500 features. So here we have like three features: area, rooms, and price. So we can have like more features: area, rooms, price. Location also is one of the feature is there. Okay, so in Mumbai, in all the bigger cities like Tier 1 cities, so the location will like change the price. Okay, so we can have location also, but then convert it into a three-dimensional. Okay, so now we'll see like machine learning and artificial intelligence model training. So train a model means we give input, we are able to give the output. Okay, back in our area and price dimension, if we give the area, we are able to predict the price. Okay, area, then it is x-axis, and price is the y-axis. Area and price, we are able to predict, like if you give the area, we are able to predict the price. So in the model training, we rely on linear algebra, because in order to train the model, we will be doing multiple matrix operations. Okay, here we are also going to use something called a linear equation. One of the most common linear equation in is the equation of a straight line. So how we're constructing this straight line? There is a thing known as y equal to mx plus c, and and we are going to learn about it later. Okay, so this is the equation of a straight line. Okay, so that is something which we are going to learn about it. So now the next thing is dimensionality reduction, which we have already seen. We have already discussed this, and that as a human we cannot visualize data of higher dimension. So instead, this dimensional reduction technique, with this dimensional reduction technique, we can use algorithm which is called PCA. Now the PCA uses this linear algebra concept, and we are again going to discuss in the future. So this is called eigenvalue or eigenvector, which you're going to see. By using this, we will be able to reduce the higher dimension into a lower dimension. And how this will happen, we are going to discuss in the future. Okay, so now neural network. In deep learning, there is a concept of neural network. Okay, so what is the neural network? In it, there is a concept of forward propagation and backward propagation. In the image below, which you can see like this is the image below, which you can which we are going to go through the scene. We have a neural network which have two input layer, which is basically two input layer, like F1 and F2 input layer. One is the area, one is called the room. We have got two input layer here, which are basically nodes in the neural network. So then we have a hidden layer. In neural network, there is something known as hidden layer, which is very important, which has three hidden neurons. So these are known as neurons. This circle things are known as neuron. and finally we have the output layer, which you can see. All of this will be reconnected. Let's consider the input feature as f1 and the room as f2, and we have an output feature as a price. Okay, output feature as a price. In neural network, we will give the f1 and f2 feature at the start as in the diagram. When this feature is sent, we will initialize some weight over here, which will be W1, W2, W3, which is there in the hidden layer, W5, W6 in our case. So here we can see that the two inputs are connected to three hidden neurons. Okay, three hidden neurons. So this basically becomes 2 by 3 matrix. So what is this matrix operations and all we are going to learn soon. So it is by 2 by 3 matrix of input and weights. The next operation which you are basically have is called the matrix multiplication, where we multiply the inputs with the weights. This is the matrix multiplication is called the matrix multiplication is called forward propagation, and backward propagation we update the weights. For updating the weights, we use something called the chain rule of derivatives that will come up in the differential calculus. Means later on it will come. Okay, so this is like this 2 by 3 matrix is there, which we are going to do, and then there is we use it in computer graphics also. In computer graphics, let's see that we have a image. Let's say that I want to represent that image in the form of pixel. Let's say that it is 4 by 4 pixel, uh, and now every value over here is a pixel between 0 and 255. If we want to talk about RGB, we will be talking about this three-dimension image like below. Okay, RGB like X, Y, and Z axis below. Let's say that if you want to perform some of the important operations on this particular image, let's say you want to scale it or rotate the image, or I want to change the image into black and white. So in all these things, we can perform this operation with the help of linear algebra, because here we will be transforming these images. So linear algebra is used to perform transformations such as scaling, rotation, and all those things. Similarly, in 3D graphics also, we want to convert a 3D model into a 2D model. You actually do this with the help of linear algebra. Then optimization is there. In optimization, we are basically solving equations. These equations are any linear equation. One of the linear equation which we have seen earlier is the equation of straight line, y equal to mx plus c. Now, if you read about one of the algorithms which is called regression, so for this y equal to mx plus c, we are going to find the right kind of m value and c value. M is called the slope and c is called the intercept. So back in the area and price, again we have come back to the area and price, where we have a lot of data points. Our main aim is to draw a best fit line, such as the line will be able to make sure that this line takes any area and predictable price and vice versa. Okay, so this line should be so good that if I take any area, it should predict the price. So that is what linear algebra is all about. So this line is very important here. Okay, so this dot which you see, this should be very close to the line. Okay, the equation of line y equal to mc square here uh, need to have the right m value and c value, otherwise the line will be created wrongly. Okay, so this is what data science is all about, to create this line, so that if I give the price, I can predict area, I can predict the price equal. So like this, like if I give the price here, so it should be, and actually it should be here, but it should be close to this thing. Okay, like this. So that is what it is all about. Okay, so so here it is all about. So we will solve this equation y equal to mc in such a way that concern that this function, and we'll see that solving this particular function, when does the error comes down. The error should come down. Like it should be, if I give some area like this, it should be like the price. If it even if it fluctuate, it should be very close to this line. So it should be like that. It should be very close to that. So we need to maximize the function and minimize the error, and this process is called optimization. Here is the concept of gradient descent will be applied. This is basically called optimizers. Okay, so that's it is. Now we are going to learn about scalar and vectors. So in this part, we are going to discuss a very important topic which is called scalar and vectors. Scalar and vectors are not only used in data science, but also in physics and math. So let us go ahead and define what is scalar. So a scalar is a single numerical value. It represents a magnitude or a quantity and has no direction. Okay, let us take some good example to understand the same. Let's say that the car speed is 60 kilometer per hour. The value of 60 kilometer per hour is basically the magnitude. In a scalar, we don't have any direction. Other example which we can consider is the temperature in Celsius. Less that it is 25 degrees Celsius, and this is only in magnitude. These two things are in the physics or normal discussion regarding to data science. Okay, so we would also see some other application of scalar with respect to data science. So let us say that we have a data set. In the data set, we have features F1, F2, F3, F3. So in data set, we'll have many records. Let us say that in the case of 5 records, we have age, marks, and attendance. So when we say with respect to scalar, this then it's a single numerical value. Let's say that we go ahead and count the number of records. In this case, I will get it as 5. Similarly, if we go ahead and say that the average feature of F1, which is age, and here also I will get some kind of a value like 12.5. The average I will get 12.5. One of the best example which we can consider in the problem of regression is a machine learning algorithm related to regression, which we have earlier also seen, simple linear regression. So in simple linear regression, we use the equation y equal to mx plus c. As we have seen earlier, we have learned m is slope and c is intercept. Over here, we will not consider m as a scalar, but we can consider c as a scalar value. The reason is that c is a single numerical value. M value here depends actually on the value of x. Okay, m value depends on the value of x. So here x is known as the vector data point. Okay, so what are vectors? Vectors can be numerical values which are bottom magnitude direction. Okay, which are both magnitude and direction, not bottom magnitude, which are both magnitude and direction. Again, this definition is with respect to physics. Okay, so but because of direction and all these things are in physics only, but we write the definition related, but we write the definition related to data science. A vector is a ordered list of number. It can represent a point in space or quantify with both magnitude and direction. First, we will look into the example with related to physics. We will look into the earlier example. Let us say that a car have a speed of 60 km per hour and is moving towards east direction. Here we have represented the speed of the car and both the magnitude and the direction. Earlier we have given only the magnitude, not a direction. That was a scalar. Now let us see that see an example with respect to data science. Let us consider an example with respect to student marks. Let's say that the first feature is IQ, second is student hours, and the third is result. So like this, IQ is 90, student study hours is 3, then the result he will fail. Okay, so like this it is there. This is what the dataset looks like. And now let's just consider two features of the IQ and the study hours. Here, if you consider this example, we can see a vector represent of IQ and study hours. So like this vector is given in this, like this is a 90 by 3. So here 3 can also be said 3 hours, and 3 is the 3 is the magnitude and hours is the unit. So this is how the magnitude is actually represented with respect to different scalar value. This unit may change. Let us another example. Here a vector representing the person weight over time. Vector for each month can be like 75, 78, 73, 70, like January, February, March, April, and the weight of the person. Many people here may think like where the direction comes into the picture. In context to data science, whenever we talk about vectors, we don't necessarily meant that of physics. In physics, when you talk about vectors, the direction is a must. But in data science, the direction is not a must. If you represent a vector in data science, it represents a collection of values. It can be in different dimension. The vectors of a person weights like this has 4 values. So it is represented in the 4 dimension. Okay. So let's say that if we represent if we represent with respect to physics and have a vector called A with a value of 1 and 2, it is in 2 dimension. Okay, so in order to see this vector in physics, we create a coordinate system. It will have x and y axis, like in below axis, below, like how we are representing it in physics. In like data science, we represent it is at 1 and 2 only. Here the first coordinate will be represented by x and the second will be with y. Okay, so 1 and 2 will be represented like this. In the image, we can see where 1 and 2 is shown. 1 and 2 is shown here. Now we want to calculate the distance between the origin and the vector. So this is the origin and the vector represented by the orange line. This orange line. Here we have used Pythagoras theorem. Pythagoras theorem, again, as I told, a lot of mathematics will be there. And here we are able to create the triangle, green line. So green line. Pythagoras theorem is, as we all know, a square plus b square equal to c square. So in this case, 1 square, this 1 square plus 2 square equal to c square. So c will be equal to and square root of 5. So the distance between the origin and the vector is square root of 5. Let's take another point b, and b again same, minus 3 and 2, and again c is the same in the Pythagoras theorem. We can see this thing. Now we can also have the vector in 3 dimension, like this x, y, and z axis also we can have. Now let's say that let's take one very good example to understand these vectors are specifically related to data science. Machine learning and deep learning, we have specifically do it with the is that we create a model. Okay, so the model takes input data and should be able to predict the output features. Let's consider the earlier example of IQ study hours, say, like this IQ study hours and this. Here, each records can represent a vector. Let's say that the record 90 and 2 is there, and 100 and 3 is there. We go ahead and plot this thing in that, like this is fail, this is pass, and all these things are there, fail, pass. So two records are there like that. Okay, now we will see how this problem will be solved. Let's say that I have some coordinates over here, and there are a lot of red colors which represent fail, and there are green colors which represent pass. So like this, like not only 2 3, we have like hundreds of students, like generally in India, and class 40 50 students are there. Maybe in the whole classroom there are more than 150 students, and we have plotted these things. Green are pass, and red is fail. So we will create a linear line between them, like a blue line. So this blue line is just seeing. Now any data point that comes below this linear line will represent the person have failed, and anything which come above this linear line will represent the person have passed. And this line can be represented by linear equation like y equal to mx plus c. Okay, this line is very important here, because anyone which comes below here is fail, anyone which comes above it is pass. That is another important concept of unit vector. Okay, in this below image, let's consider the data point is 3 3. Okay, a unit vector is represented with this is, you can Google it also, use this thing. Unit vector has a magnitude of like 1. It's basically means that I have this as unit vector towards x-axis. Okay, unit vector towards x-axis, and it will be known as I. Okay, so then we have j, green line j. We have this green line j as a unit vector towards x-axis. Okay, so it should have been like 1 dash. Okay, so 1 is the unit this is the towards the x-axis, this is towards the uh, j-axis. Similarly, if I say 3 unit vector towards 3 units vector towards um, y, then I am moving 3 points toward x-axis, like 3 is 3 points toward x-axis, and 3 points towards the axis. So it will be represented by 3i plus 3j. So this I and j are specifically nothing but unit vector towards x and y axis. So this is again a very important thing to know. And addition, now we'll look into addition of vectors. Okay, so addition of vectors is very important. In this part, we are going to discuss about the addition of 2 vectors. So we are moving towards a mathematical operation that we have specifically applied to vectors. Let us say the 2 vectors a and b are there, like this vectors are there. Now we need to perform operations of addition, which is a plus b. So like this addition will be easy as we will add x coordinates with the y coordinate. Let's like it is very easy if you like just do the addition. Let's see that how it looks in the coordinate system. Okay, so and the image, so everything is very important to look in the coordinate system also. So addition of 2 vectors is like traversing from one vector to the other vector. In our case, how we traverse from -4 3 253 minus 43 is like this thing. 253 is this. For this, we will traverse from -4 to 5 units in the x-axis, and from 3 to 3 units in the y-axis. This will give us a result as 1,6. So we are traversing like this. In this direction, we are traversing the whole thing. Now let us see in respect to data science, where exactly we use the technique. We use the data aggregation and feature. We use it in data aggregation and feature engineering. By this we mean say we have two sensors and they give two data points like this and this. Then we will add them to get 5, 9, and 13. It is also uses NLP, natural language processing, word embedding, images processing. In this, let us see in the word embeddings. Here we'll see that the example of converting text into vectors. Let's say that we have two words for data and science. Like this, we have two words for data and science. Science is represented by this. If you want to combine a data science, the vector, we will just add it and it will become like this. Okay, so this is what we have learned in the part 1. Like we're going to see more data operations in the part 2. Thank you.